Welcome back to ch205. In this video, I'll be talking about solving ordinary differential equations, or ODE, with two boundary conditions. So the difference between this chapter 6 and other chapters, specifically chapter 5, is that in chapter 6, we're going to look at two boundary conditions for one-dimensional problems. In chapter 5, we always had one boundary condition, like we had a system, maybe if you remember the species, three-species problem, or the pendulum problem, right? So all of the boundary conditions actually are given on one side, either one or two. In chapter 6, we're going to look at boundary conditions that are given on both sides, like at x0, one is at x0 and the other one is, let's say, at x1, or and one is at x0, the other one is like half in the middle of the domain, let's say x equal 0.5. That means the two boundary conditions are not given all at one point. Okay, so that's another difference. In the pendulum problem, we saw two boundary conditions though, but both of them actually were on one side. Like we had the initial angle of the pendulum and the initial velocity of the pendulum. So both of them are at t0. Or in the species problem, we had the species concentration of A and B and C at time 0. Right? So all again at time 0. So on one side of the boundary, if my variable is x-axis, or the independent variable is x-axis, one side of boundary means t0. Two sides of boundary means one is t0, the other one is, say, t something else, like the other side, where the time is maximum, right? So we're going to deal with this case, the two different boundary conditions on both sides of the domain in chapter 6. So we're going to start with a generic equation, like imagine we have a second order differential equation like this in equation 6.1. Right? The second derivative of y is equal to some function of x and y, and I have two boundary conditions. And now you see that the boundary conditions are given at two x values. One is at x1 and the other one is x2. Okay? So this causes a problem because when you solve the problem, let's say using the technique we learned in chapter 4 or 5, then you're going to use one of them, right? And then you start with that cell and create other cells, and then you march along the path, the domain, until you get to the other side of the domain. But once you get to the other side of the domain, you see that the boundary condition is maybe not satisfied, and then there's a headache because we need to satisfy both boundary conditions. So we're going to look at this problem specifically. Let's say we want to look at the heat conduction in a rod, and the governing equation is like this. It's a second order differential equation of temperature T with respect to x. So if you solve this equation, T would be, down the road, the distribution of the temperature along the rod. For every x, we should be able to know how much the temperature is, right? Okay, so the other variables are constants. H is the heat transfer coefficient. This is given. D is the diameter of the rod. K is the thermal conductivity of the rod. And TA is the ambient temperature. Okay, so all others are problem constants. We are about to solve T as a function of x. Okay, so we'll learn how to do this in chapter 5. If we have a second order differential equation like pendulum problem, we convert it to a system. Each is first order differential equation. So how we can do this? Oh, by the way, imagine we have the boundary conditions, one at x0 is 100 degrees and the other one is 1, the temperature at 1 is 0. So imagine you have a rod, one endpoint, let's say, is you're putting one endpoint on ice, so the temperature is 0, and the other point is, let's say, boiling water. Okay, so at one point, or one end of the rod, the temperature is 0, the other end is 100 degrees, and you want to see how the distribution of the temperature is along the rod. Okay, All right. So the first method we're going to look at is called shooting method. This is for solving differential equations where we have two boundary conditions on both sides. We do not have both boundary conditions on one point, right? Like in this case, temperature is known on 2 points of the boundary. One is 0, one is 1. Okay. Again, I'm just emphasizing this because this is very important. In chapter 5, we had either temperature at point 0 or temperature at point 1. We didn't have temperature on both points. Okay? Alright, so let's look at shooting method. So what we do in shooting method? Well, the initial part of the approach is pretty much like in chapter 4. We have to convert the second order differential equation to a system. And to do that, we're going to assign a new variable called f. Okay? And let's call f as the derivative of t with respect to x. I'm going to convert the second equation, the second order differential equation, to convert this into equations of t and f, right? Okay, let's see. So the second, if f is the first derivative of t, then the second derivative of t with respect to x is going to be the first derivative of f. So here is the second derivative of t with respect to x, which is the first derivative of f with respect to x, is equal to the right-hand side. So far I just rewrote the first equation in terms of f, right? Well, part of it is in terms of f. The left side is in terms of f, and the right side still is in terms of t. Okay? Alright, so what is the second equation? The second equation is the one we just came up with, and that is f is equal to df f is dt dx. Okay, I have two equations, and what are the boundary conditions? Well, at t0, at 0 temperature is 100. At 0 I don't have any information about the f, which is the derivative of t. I do not know what this is, so I just put a question mark here. And then the temperature at 1 is 0. Okay? Alright, so these are the boundary conditions I have. And we're going to go ahead and solve it. So we see that we have two equations, each is first order, and that's a system, right? I have to solve for f and t together. So that reminds me the technique we learned in chapter 5. So let's go ahead and use forward Euler to solve it. Okay? So I'm going to jump in directly to the spreadsheet. So here is the solution for the heat conduction problem in the rod. These are the problem constants. H, D, K, right? You can also go ahead and calculate 4 times H over dk using these 3 constants to make the life simpler down the road. And then TA is the ambient temperature and dx is delta x. Okay? So I want to solve the problem, the temperature distribution from 0 to 1. So I split my interval from 0 to 1 with the separation of delta x, which is 0.1. Because I'm going to have 10 points along the way. Including the two boundaries, it's going to be 11 points, or 10 intervals. Alright, so the first point is boundary condition. Well, here's the problem. We usually start from, let's say, x0, and for x0 I should know u0 and t0, right? By the way, this u is actually f. According to textbook, this should be f. I'll just call it f. Okay? So at t0 I know t, which is 100. Where is it? So at t0, at x0 I have t equal 100, but at x equals 0 I don't know what f is. That's the problem. But I do know t on the other end, at equal 1 is 0. So here, this guy is an unknown. So how can I start without knowing what f is initially? Okay, so I'm going to make this a black box so far. So make it black. I don't know what this is. Well, maybe make it red. Red is better. Okay, I don't know what this is, so I'm going to make a guess. Let's say this guy is -1. I'm just guessing it. Okay? Initial temperature is 100. Well, temperature at x equals 0 is 100. Then I can go ahead and do forward Euler. For forward Euler, you can go ahead and discretize these two equations, right? So if you discretize the first one, then very quickly I'm going to do the first. Okay. So let's write it here. Then f at n plus 1 is going to be f at n, and then plus dx, and this actually is supposed to be plus, okay, dx times 4 times h divided by d divided by k times t at n minus ta. So here is the forward Euler version of the first equation. You can go ahead and discretize the second one using forward Euler. So which means this guy, right? So then t at n plus 1 minus t n is going to be, or that's equal to tn plus dx times f at point n. So I have two equations for these two. I just convert them into forward Euler. I'm going to hard code these guys into my spreadsheet. Okay, the initial conditions, I have to put some numbers. This is this is an unknown, so I put -1 because I don't know what that is. The problem is not given. In the problem, this is not given. And initial temperature is 100. The second one, using forward Euler, is going to be the previous f, right, which is B9, the blue cell, this one, which I made red, and then plus dx, which is B6, is this one, times 4h divided by dk. So here is 4h divided by dk is the purple, right, so times that, and then times T minus the ambient temperature. Well, the current temperature is the purple cell minus ambient temperature is the green cell right here. So that's the equation for f. And then the equation for T is going to be the current T, the blue cell, plus dx, which is the green cell, times times f, right? So let's go back and look at the equation one more time. So Tn plus 1 is Tn plus dx times Fn. And so this is what I have. Tn plus dx times Fn, right? So B9 is Fn. F at the previous point, or F as the current point. Okay. So this row that we're sitting on is at row n plus 1. So we're going to hit enter. Okay, I have these two written. You can drag down, and this is what you get. You plot. Okay, so here's the blue line. So this is T against X. Okay. The problem here is we know that the temperature on the other side should be 0 because the other point is on ice, right? But the way I solved it, the other side has a temperature of 822.7. It's not 0. So what has gone wrong? Well, my initial guess is not right here, the red cell. So how can I do this? Then I'm going to do gold seek. I'm going to do gold seek on the other end by changing my guess. So I'm going to go to data. What if gold seek? I'm going to do gold seek on this cell by set that to 0. And I'm going to change my guess such that this becomes 0. So watch this blue line as I hit OK. You see, now it solved it. It's changed my guess. Initially it was -1, now it's minus 200 something. And then at the other end temperature is 0. So now it matches the two boundary conditions. Here's boiling water, here's an ice, temperature is 0, and then this is the variation of the temperature along the way. Okay? This is backward Euler version of it. Okay? So I hope this is useful. Stay tuned for the next video and backward Euler version of this, and see more problems using two boundary conditions and two endpoints of the problem.